I think we can start. So, before the talk itself, let me go through the usual technical stuff, which I think people know by now, but this talk is being recorded and we will post it on YouTube eventually. So please bear that in mind if you want to ask questions. If you want to ask any question during the talk, please either unmute yourself or if you have a problem with your audio or you don't want to, for any other reason, just type it in the chat and either the speaker will read it or I will read it out for him. And yeah, there will be time for discussion at the end, and we even usually stop the recording, and there is a part for any informal comments. Okay, and now it's my pleasure to introduce our speaker today, Marcus Michelen from the University of Illinois at Chicago. And Marcus will talk about roots of random polynomials. So Marcus, please.
Great, yeah, thank you for the introduction. And thanks to the organizers for the invitation and everyone here for coming. So I'm going to talk to you guys today about some joint work with Julian Sahasrabudhe, who is a postdoc at Cambridge, who I now see just his face appeared on the right side of my screen, so he's here as well. So I also want to point out, I can see your questions in the chat. So if you are sending a message in the chat, I will be able to see it and address it live. So my goal for today is to talk to you about some new results about the roots of random polynomials, in particular those especially close to the unit circle, and maybe also along the way provide a slightly more combinatorial intuition for what's happening in these roots of random polynomials. So to begin with, what are the random polynomials we're looking at? Well, sort of as you might expect or hope, it's just going to be a polynomial where the coefficients are IID. So these are going to be independent, identically distributed random variables. Throughout the talk, we're going to assume that they're all mean zero and finite variance. And for most of the new results, we're going to be considering when they're standard Gaussians or standard normal variables. We will talk a little bit about when they're like IID plus minus 1, or maybe -1, 0, or 1, or things like this. But for the most part, you can always sort of think of them as Gaussian random variables. And our guiding question is, how do the roots of a random polynomial typically behave? This is going to be the guiding question both for our history section and for our new results. So let's start with talking about real roots. So maybe let me go back very quickly a little bit here. These are random polynomials with real coefficients. So it seems sort of plausible you might have some number of real roots, although it's not necessarily obvious how many of those you might have. Now, if we let n be the number of real roots of this polynomial, let's go through a little bit of the history here. So this definitely predates what we think about as probability, but as early as the 1780s, Waring pondered the number of real roots of a typical cubic. Of course, he didn't prove anything, but he wrote down some sentence like, it appears in most polynomials of degree 3, like 75% of them have all real roots or something like this. Of course, nothing was proven, but he was already thinking about how many real roots does a typical polynomial have. And this started in earnest in 1931 with Bloch and Polya, and they considered the case when your coefficients are -1, 0, or 1 uniformly at random. They proved an upper bound for the expected number of real roots. So they prove an upper bound just of root n, and we'll see in a moment this was improved by quite a bit by Littlewood and Offord in their famous series of papers. So for various different coefficients, they showed with high probability you have at most log squared many roots, and you have at least log over a triple log of n many roots. And from here, Katz in 1943 found an exact expression, the exact number of real roots for a Gaussian. So he wrote down an exact integral for this expected value when the coefficients are Gaussian. And then by analyzing this integral, showed that you have on the order of log n roots. And in fact, you can compute the explicit constant out from it. This is sort of a quick history of how many real roots a typical polynomial has? Well, it's on the order of log n. So from here, people are really off to the races. So Kac proved this for Gaussians, and he thought, well, it seems pretty likely that my proof will also work for various other coefficients. So it took him 5 more years to show the same thing when your coefficients are IID between -1 and 1. So in fact, there was quite a bit of work that had to be done. And his exact form for the expected value really did depend quite a bit on the coefficients being Gaussian. It's far more tractable in the case when the coefficients are Gaussian. So after Kac proved this for uniform between -1 and 1, Erudish and Alford proved it for discrete random variables, -1 and 1. And here, they weren't able to show an exact form for the expected value, although the Kac formula does give you such a form, it just isn't necessarily super tractable. What they ended up doing here was counting sign changes in very small intervals. And then in the 60s and 70s, Stevens and Ibragimov and Maslova proved that this expected value being asymptotic to 2/pi log n still holds for a wide family of coefficients. So for instance, if the coefficients are mean 0 and variance 1, then this is still going to hold. It's a little bit technical, but they even prove it for a wider family of variables. You just need the central limit theorem to hold. So it looks like the expected number is on the order of log n. There's still quite a bit more that can be shown. So Eilman and Koslin, in the case of Gaussian coefficients, in a really lovely paper, computed higher order terms of this expected value. They took a totally different approach from the Kac approach, and they do something very geometric. So they're able to show that you have a log as your first term, and then your next term is a constant, and then you decrease in powers of n for the next few terms. Maslova also showed for mean 0 variance 1 coefficients that the number of real roots has a central limit theorem. So the mean is on the order of log n. I don't remember exactly what the variance is, but you end up with a central limit theorem of a mean and whatever this variance was for the number of real roots. Maybe the last real root result I'm going to mention here is Dembo-Punin, Shao, and Zaytouni found sort of the lower tail for number of real roots. So if you give me, let's say, k equals 10, they calculated the probability you have exactly 10 real roots. This decreases as some power of n. So this is just a quick history of what goes on for the real roots. The moral of the story is you have some number of real roots, and it turns out that that number is log n. So a quick detour while we're talking about real roots is talking about an adjacent question. Similar to asking about real roots, you could ask about roots of random trigonometric polynomials. These will come up in a moment when we're talking more about the complex roots of the polynomials I play. So if I take a sum of cosines and sines, where my coefficients now are IID, then if I look at the number of roots of this guy between 0 and 2pi, of course this is periodic, so if I look bigger than 0 to 2pi, I'm just double counting stuff. Qualls computed this expected value exactly. And you get a really nice exact closed form here that I've written down. And this is asymptotic to 2/√3n. So you have on the order of n roots for a random trigonometric polynomial. So now, having both the cosine and the sine is nice. You end up getting something that's stationary. So if I replace theta with theta plus h, I get something with the same distribution. But if I just look at the cosine or sine series, Dunnage, so this was earlier, proved the same asymptotic equality for the expected value for number of roots. So for a random trigonometric polynomial, you have on the order of n roots. And we'll discuss later on how you might show this identity that Qualls has here. And then in the case in which your coefficients above are Gaussian, Granville and Wigman showed a central limit theorem for the number of roots, and they showed that the variance is linear. I don't want to get too deep into this, but there was a recent paper, I believe from 2019 or perhaps 2020 by Do, Win, and Win, which showed that the variance for the number of roots of this type of a polynomial actually depends on the distribution of the coefficients. So for Gaussians, it's some constant times n, and for plus minus ones, it's a different constant times n. This is an instance in which this universality sort of begins to break down. Okay, we've spoken about the real roots. and there are only log n many real roots. So that means the vast majority are complex roots. Let's begin to talk about those now. So Hammersley and Sparrow and Schur showed that most roots of a random polynomial are near the unit circle. Here's a quick picture of that, of degree 120, and this is a case of Gaussian coefficients. And I want to point out a few things about this picture that are going to be sort of recurring motifs. So first, most of the roots are near the unit circle, but not literally all of them. So what this statement is saying is that if I look at the proportion within epsilon of the unit circle for every fixed epsilon, then this is going to converge to 1 for every fixed epsilon. There will be some stragglers in the case when we have Gaussian coefficients, and we'll talk about what those stragglers might look like in a moment. I also want to point out that not only do they converge to the unit circle, they converge to the uniform measure on the unit circle. So if I look on any arc of the unit circle, the proportion that are going to converge near that arc is going to be the correct proportion. Maybe the last thing to point out is, since our coefficients are real, our zeros are going to be symmetric when I conjugate. So everything above the upper half plane looks exactly the same as what's going on below it. Oh, and actually, maybe one last thing to note is we'll notice that things are like really spread out, in the sense that it looks like these zeros are going to repel each other. That's going to be another recurring motif we'll see in a lot of these figures, that the zeros of these polynomials do tend to repel each other. And we'll talk about how to quantify that when we get into the proof of our results. Okay. So this convergence to the unit circle happens if and only if your coefficients have a log moment. So this is an extremely universal behavior. Any reasonable distribution you could possibly think of is going to have this sort of behavior. So we know most roots are going to converge to the unit circle, but I haven't told you anything about what the scale is. So again, we know that all of our roots are going to be within epsilon of the unit circle for every fixed epsilon eventually, or the vast majority of them will be. But at what rate can I take epsilon to 0? So Shepp and Vanderbei in 95 showed that most roots are on the scale of 1 over n away from the unit circle. And what this means, in the sense they proved it, is the expected proportion within c over n is going to tend to 1 as c tends to infinity. So they found a very nice function for the limit of the expected proportion of roots within Cn of the unit circle, and you can just evaluate exactly what happens when you take c to infinity. So really, the bulk of the roots are going to be on the order of 1 over n away from the unit circle. So they used methods similar to Kac's, in the sense that they found, in the case of Gaussian coefficients, an exact expression for the expected number of real roots in a given set. So let's talk a little bit about those stragglers now. So Perez and Varag, in a really lovely paper, showed that roots uniformly bounded away from the unit circle tend to what's known as a determinantal point process. So let me show you a couple of pictures here, taken from Perez and Varag. On the left, we have a determinantal point process. We can see things here are very spread out. Things are very explicitly repelling each other. And on the right, we have an ordinary Poisson process, which is essentially placing points of a certain density as randomly as possible with no correlations between them. So there's a technical definition of this determinantal point process. It's a very special object. And without getting too deep into the weeds, and if it's confusing, don't stare too hard at it. A determinantal point process in this instance means the density of having zeros at certain points converges to this determinant. It's a very special algebraic expression for the density of having zeros at certain points. And this is what governs the law of zeros away from the unit circle. So this is a really lovely paper. This is essentially a miracle in a lot of ways. This is a very extremely special object you end up with at the end. It's not necessarily super obvious right away, but this is not going to hold if I look at real roots. It's impossible for this type of an identity to hold just because we have this conjugation happening above the upper half plane looking below. So sort of in that vein, let's discuss how this behavior should be really not universal at all. right? So
Sorry,
if you take a, yeah.
Sorry, Marcus, I'm not sure I understood you're looking at roots which are some epsilon away from the unit circle.
Here I'm looking at roots that are macroscopically far away from the unit circle.
Yes, yes. So they are and then you take a little box which is within the ring from say epsilon and to epsilon, or what
So you mean for this picture?
Well, no. What do you mean that they about this determinantal point process? So, for example, I know that the roots can't then be close to the circle, whereas the determinantal point process can be everywhere, right?
Yeah. So this is governing the roots. So this exact form is for roots inside the unit disk. So in fact, there will be some stragglers outside the unit disk. Sorry, not near the unit circle, is what this is actually saying. This is telling you what happens for the small number of roots that aren't in a small band of the unit circle.
Yes. But when you look at the, say, inner circle, like you look at the ball of radius 1 minus epsilon.
Yeah.
Then would you, for example, does this mean that the roots are uniform? I'm not looking at a joint distribution, but just at one root out of those that fall in that. Are they uniform there?
They will not be uniform there. Yeah.
Yeah, that's what I was expecting. But this determinant point process, that would give you a uniform distribution, right?
Well, this is depending on the modulus of the root. So if you plug this in for one root below, then you end up with a function that's going to depend on the modulus of the root. And you'll notice it's blowing up near 1. So if I plug in zi and zj being the same root, then I end up with 1 over pi times 1 over 1 minus the modulus of it squared.
Okay.
So in fact, this will be less concentrated near 0 and higher concentrated near 1.
Yeah. Mm-hmm. Yeah. Thanks.
Okay, great. Any other questions on this result? Okay, great. So on that note, that's a great point to point out that this behavior is very far from being universal. And you could even think there are like totally banal reasons why the story we just discussed can't happen for arbitrary coefficients. Right, so here's a picture, maybe describing something very similar to what Jan was talking about. Right, I can have a root very far away from the unit circle. And if I replace z with 1 over z, this shows that the roots far away from the unit circle are going to be in the same distribution as the roots within the unit disk. So having a root very far away from the unit circle is similar to having a root very close to the origin. So for Gaussians, with positive probability, you will see a picture like this. So I had to resample this, I don't know, maybe like 20 times, but it wasn't really a super crazy number. But conversely, if my coefficients are plus minus 1, then deterministically, all roots have modulus at most 2 and modulus at least a half. So this behavior will never occur. So even just for this basic reason, the behavior of roots very far from the unit circle will not be universal. Okay, so we've discussed how far roots can get and also how roots typically are. And Shepp and Vanderbei made a conjecture about how close roots can typically get. So they made a pair of conjectures in the same paper from 1995. They conjectured that for the case of Gaussian coefficients, you have a root within 1 over n squared of the unit circle. And if I rescale on the order of 1 over n squared, then the modulus of those roots converges to a Poisson process of some intensity. And they conjectured the same thing for real roots, except on the order of 1 over n. So they suspected that you would have a root within 1 over n of the unit circle that's real, and also that you get convergence to a Poisson process when we rescale properly. But shortly after this, 2 groups in slightly different notions showed that 1 over n squared is the best possible rate for part A. So in the sense that they showed you can't make it smaller because there's a positive probability you have no roots within epsilon over n squared for some fixed deterministic epsilon. what I'm going to talk to you about is a resolution to both of these conjectures. So first, we're able to show that the complex roots indeed behave the way that they expected them to. So if you take a random polynomial with Gaussian coefficients, then the roots are going to tend to a Poisson process when I rescale on the order of n squared away from the unit circle. So in particular, this says if I look at the nearest distance from a root to the unit circle, that'll converge once I rescale by n squared to an exponential random variable. And we can compute the rate of this just directly from the Poisson process above. So this says typically you have a root on the order of 1 over n squared away from the unit circle. And we're also able to show that the corresponding conjecture for real roots unfortunately does not hold as they stated it. So you do have a real root within 1 over n away, but you do not get a Poissonian limit. So in fact, the limit when you rescale properly is a non-Poissonian point process. So we'll discuss why that occurs later on in the talk. But yeah, so the moral of the story from these two results is for the complex roots, you have a root within 1 over n squared, and the law governing the distribution of those away is a Poisson process. In real roots, there's 1 over n away from the unit circle, but it's not a Poisson process. So I have here an extremely lovely picture my collaborator drew that demonstrates sort of the regimes at play here. So in this giant black line here, we have the unit circle itself. Shepp and Vanderbei showed that the bulk of roots, so the vast majority of them, lie within 1 over n. Perez and Varag told us the law of roots that are especially far away from the unit circle, so macroscopically far away. And we're handling the roots that are atypically close to the unit circle. So we could think about these as Shepp and Vanderbei telling us about the bulk, Perez and Varag about the upper tails, and us sort of about the lower tails of the distribution of roots near the unit circle. Okay, so before we jump in to talk more about how we might prove these results, does anyone have any questions on them? All right, so we're going to give you a sketch of the heuristic for how we prove this. And that'll also give us a combinatorial heuristic for why roots are close to the unit circle in general. I want to start first with sort of the classic sketch of why roots are close to the unit circle in general. And maybe we can see how we can think of a more combinatorial way of thinking about this. So why do most roots converge to the unit circle? So complex analysis tells us that if I want to count the number of roots of a function in a disk, I can just look at this integral here. Right? And this is known as the argument principle. So now the way that we think about this is if I look at some modulus bigger than 1, then the fact that my coefficients are random means that the top term in my derivative and my function itself should more or less dominate. There can't be any massive conspiracies between the lower order coefficients to build up to beat these bigger coefficients. So that means we'll roughly have this following expression here. And now we just naively plug this into the argument principle, and you basically get that the number of roots within, let's say, 1 over epsilon of the origin is going to be on the order of n. Of course, I'm being quick and dirty here. This is sort of a quick sketch of why this occurs. And you can do the same argument if I look slightly less than in the unit circle. So I look at a disk of radius 1 minus epsilon. We can show that the number of roots is going to go to 0. So this is, again, a quick and dirty sketch of this proof. This is rigorizable in a not too crazy way. It's a bit in the weeds, but instead of looking at this argument principle, you might want to look at integrating the Laplacian of log modulus f. This is an approach that will show you that the 100% of your roots will converge to the unit circle. So let's say we talk about a slightly different heuristic than this. I think this is a good heuristic if you've really internalized complex analysis. This definitely shows you what's happening, but maybe it doesn't tell you a story for what's going on. So let's try to come up with a more combinatorial story of why roots are so close to the unit circle. So let's start with a totally banal observation. So a complex zero is just when the real part and imaginary part of my function are zero at the exact same time. And now let's see what happens if I look at the real part of my polynomial on the unit circle. So if I look at the real part on the unit circle, we end up with one of these trigonometric polynomials that we saw earlier. And we know that this has on the order of n many zeros. And if I look at the imaginary part, we have on the order of n many zeros as well. And now let's think about if I'm now looking instead at the circle of radius r equals 1, and I look at a slightly different r, all of these zeros are going to wiggle around a bit. Right? And now typically, if I move my radius by a factor of dr, a typical zero is going to move on the order of dr. So the idea is we're going to maybe think about having a bunch of roots placed down, wiggling our circle, and maybe some of them might collide with each other. So with this in mind, let's go into a totally heuristic mindset here. So let's place n red balls uniformly at random on the unit circle and n blue balls uniformly at random on the unit circle. So I'm going to think about the red balls as the roots of the real part and the blue balls as the roots of the imaginary part. And now a typical ball, if I've done this totally randomly, is going to be on the order of 1 over n away from a ball of another color. But a few will be on the order of 1 over n squared. And if I look at, let's say, big constant over n squared, I'll get even more, but still sort of a fixed number depending on that constant. And now, if I look at the circle of radius 1 plus h over n squared, then each ball is going to move on the order, roughly, of h over n squared. So that'll imply that some of these red balls will collide with some of these blue balls and tell us that a zero should occur. And now, since most balls are within 1 over n of a differently colored ball, this suggests that most collisions that occur will happen by time big constant over n. So this is a heuristic for understanding both why there should be some roots within 1 over n squared away, and also a heuristic, although a little bit of a sketchier heuristic, for why you should see a lot of roots on the order of 1 over n away. So I'm going to get into, in a moment, a few aspects of this heuristic that we obviously have to adjust because roots, are not uniformly distributed, but this is actually the heuristic that sort of governs our proof. So let's dig in to some wrinkles in this heuristic. So most obviously, right, the roots of the real and imaginary part are certainly not placed just uniformly and independently at random. So here are a couple of pictures. I said below on the left which one is which, but even from these pictures, you should maybe be able to tell the one on the right is when I have red and blue uniformly placed at random with no interaction between them. And on the left is when I have the zeros of the real part in red and the imaginary part in blue. So there are a few things we can note, and maybe the clearest one is the repulsion that's happening between roots on the left is forcing it to be sort of uniformly spread out. Like there are no big intervals with roots missing, sort of because of this reason. If we also look on the left, you'll see that not only do balls of the same color repel each other, but also balls of opposite color repel each other, and there's even a slight bit of interlacing that occurs. That's just because the derivative of one of these is going to correlate with the derivative of the other, is why we have this interlacing. So a couple of other wrinkles in this heuristic. The zeros of the real and imaginary part do not move at equal rates. So here I'm putting move in quotes. That's when I'm thinking about changing my circle from r to, let's say, r plus epsilon. The amount at which they move is going to depend on the derivatives of the real and imaginary part evaluated at those zeros. Now, as we look at circles further and further away from the unit circle, so I look at a radius much, much bigger than 1, then this behavior is going to become less governed just by the behavior on the unit circle. So sort of higher order things are going to end up coming into play, It's not just going to have roots moving sort of at nice velocities. So the last point, which is not super important, is that the Cauchy-Riemann equations are going to tell us that nearby roots can never move in parallel. They can only attract or repel each other, which means that if I look outside the unit disk, they'll get closer to each other, or if I look inside the unit disk, they'll get closer to each other. Okay. So with this heuristic in mind, let's talk about how this proof goes in a very high level chunk. So we have two halves to this proof. The first one is showing that the heuristic is viable. I know this is a lot of text, but all we're saying here is if I look at the point process we want to compute, which is I look at the roots of my polynomial near the unit circle and rescale them properly, then we want to show that I can approximate this measure with one that only looks at pairs of roots on the unit circle that should collide to give us a root in the right place. So we want to show we can take the measure we care about and replace it with a measure that depends only on the behavior on the unit circle. So the first big chunk of our proof is to show that for any given set, these two agree with high probability. So this reduces, you can think about it, a two-dimensional issue. So thinking about zeros in a complex plane, to thinking only about the behavior of these trigonometric polynomials on the unit circle itself. And the next thing we need to do is use the method of moments to show that this auxiliary measure converges to a Poisson process. And that we use the method of moments for. And that's in many ways a typical sort of thing when you do convergence to a Poisson process. There are many aspects of this that are quite difficult in this case, and we might be able to talk about them, time permitting. Okay. So let me maybe very briefly mention how you can show the heuristic is viable. So really the main point here is if I just look at the real part on some circle of some radius, I can just Taylor expand in terms of the behavior on the unit circle. And the moral of the story here, right, is if I know I have a zero on the unit circle, right, then I can see how this zero moves as I vary r. In other words, this ratio of derivatives here tells me the speed. And now we can do the same thing for the imaginary part. And now again, I know this is getting to be a little bit too much text on a single slide at once, but the point of writing this down is we can write down explicitly what this auxiliary measure is. It's counting the pairs of zeros of the real and imaginary part in the unit circle whose derivatives behave in a way such that the two roots will collide in the right place. And then we just show that this basically matches the number of roots in the sets that we care about for any given set. Okay. Let's talk a little bit about how we can do this method of moments. So what we're going to end up using are the so-called Kac Rice formulas. This is an exact integral formula for the zeros of a Gaussian process. This is what I alluded to in the past that Kac used to count the expected number of roots of a random polynomial, and also Shepp and Vanderbei used in their study of where the bulk of these roots are. This is a general statement about Gaussian processes. It says if I give you a sufficiently nice Gaussian process, the expected number of zeros in an interval is exactly equal to this integral. So I'm going to break down this integral in a moment. I just want to point out this is something you can compute each aspect of this pretty explicitly. This numerator is just going to be some expected value of some Gaussian. So that's something we can write down. The denominator is just a variance, and we know how to write something like that down typically. This is definitely painful to prove, but there's a reasonably nice heuristic proof of this. I am going to mention very briefly a heuristic for understanding this. I think this is a nice sort of self-isolated moment. So if I've sort of lost you in the talk up to this point, and you want to get at least some tiny thing to take away from this, this might be a nice couple of slides to look at. So I'm going to explain sort of in isolation how you might show something like this and where this formula is coming from. So let's remember, we want to show the expected number of zeros of some Gaussian process in I is going to be this exact integral. So we're going to end up using a linearity of expectation here. So I'm going to count the number of zeros in small intervals and then add these up for a bunch of small intervals. So first, if I give you a small interval, right, the probability I have a zero in that interval is going to roughly be the probability that we change signs on that interval. So that just means that the value of g on the left and the value of g on the right are going to have different signs. So I can Taylor expand my right endpoint in terms of my left endpoint. And now let's condition on our derivative and just assume for now that the derivative is non-negative. So now, if I want to look at when I have a different sign, it's going to roughly be when my left endpoint lies in this set. It has to be between negative width of my interval times the derivative and 0. But now g is a Gaussian and h is small, so we can compute this probability pretty closely. Right? So h is small, so this interval is basically a small interval around 0. So it's just the density of the Gaussian at 0 times the width of the interval. So this is roughly h times the absolute value of the derivative times the density at 0, which is just 1 over root 2 pi variance. So now I take expectation here, add these up over all my small intervals, take the width of the interval to 0, and I go from a sum to an integral. And then you're off to the races, and this is what you get. So you get this type of an expression by counting sign changes on very small intervals. And now I want to point out that this is telling us that the derivative wants to be big when I'm at a 0. Right? If we look at this probability we calculated in the middle of the page, right, this probability is going to be bigger if g prime is bigger. So this is saying if I look at a random polynomial, or just a Gaussian process in general, and I look at a 0, then its derivative is going to want to be even larger than usual. So now, this is going to tell us automatically that we have this repulsion that I've alluded to a couple of times now. Right? So Kac Rice is saying, if my derivative is small, I'm less likely to be a 0. So in particular, if I have a 0, my derivative wants to be large. But now let's think about what happens if I have two zeros close to each other. Right? If I have two zeros close to each other, the mean value theorem tells me that my derivative has to be small. So these two forces are exactly pushing up against each other. And this is why we get this nice repulsion when we look at images of zeros of random polynomials. So I explained this in a one-dimensional case, and this picture is a two-dimensional case, but the same story still holds true there. So we have this repulsion between roots of random polynomials just because of this fact that at zeros, the derivative wants to be big. Okay, so I have around 10 minutes left. So maybe let me mention very quickly how the rest of this proof goes down for the complex roots. And I'll say a couple of things about real roots. So let's remember, we want to calculate the moments of a certain measure that we've defined only in terms of behavior on the unit circle. We're going to want to use the method of moments to show convergence to a Poisson process. So how this goes down is you want to look at a lower factorial moment. And we want to show that this converges to length of the interval over 12, because that's the intensity of our process, to the kth power. So the Kac Rice formula, which gives us this expected value of number of roots, also works for these factorial moments. We can write it down as a certain 2k dimensional integral. And now we have to just analyze this kernel here. So this density is going to correspond to having roots let's say x1 through xk and y1 through yk, corresponding to the correct complex roots. So again, I'm just going to mention this very briefly. When you want to show maybe convergence to a Poisson process, we usually want to show about three things. So you want to show that if I look at points very far away, that the correlations decay, and it looks sort of just like independent copies of the one-dimensional version. Then we want to show that the mean is correct. And then we want to show sort of that points that are very close to each other don't dominate this integral. So you can think about this as working sort of with like weakly correlated random variables of some kind. So sort of the zeros that are close to each other are maybe slightly correlated, or our third point says they don't contribute too much to the expected kth power. Maybe I'll skip what's happening for how we show this. This third point is really what takes up the bulk of the paper. This is our sort of most technical contribution to this result. Maybe I'll skip this fact here. Maybe I'll summarize what happens, right? So the summary for how complex roots goes down is we look at a new measure in terms of roots on the unit circle, and then we think about how they might collide as our circle varies from being of radius 1 to 1 plus epsilon, where epsilon's in the order of 1 over n squared. Then we show the two measures agree on any given set with high probability. Then we use the method of moments to understand the moments of this new measure. And we show this converges to a Poisson process by analyzing this density. We show the density factors into sort of the one-dimensional copy when everything is spaced far enough apart. And then we show it has the correct mean. And that shows that we get convergence to a Poisson process. So this is the story for how we show this convergence of complex roots. Okay. Let me maybe mention one extra thing we get to pick up as gravy here. Right? This also shows that the roots close to the unit circle are going to be roughly equidistributed. So you get a Poisson process, and in fact, the arguments of them is going to be uniformly placed. So here's a picture. In red on the left, I have the roots close to the unit circle. And then I've done a transformation on the right where my x-axis is the distance to the unit circle when I rescale, and the y-axis is the argument of these roots in red. So they are uniformly distributed, and you get a two-dimensional Poisson process if you look at it like this. Okay. In the last 5 minutes, let me maybe tell you a few facts about how the real root story comes down. Oh, I'm sorry. Before we do that, I want to point out one sort of question that's still on the table. Everything I told you about for complex roots really depends on the coefficients being Gaussian. So we wrote the proof for real Gaussians, but it also works essentially verbatim for complex Gaussians, although without this symmetry above and below the real axis. So it's still open whether or not this holds for arbitrary variables that are mean zero variance 1. We expect the answer is yes, but our methods don't give that. They really do depend on this Kac formula, which uses the fact that the coefficients are Gaussian very deeply. Okay, and now let's discuss very quickly what happens for the case of real roots. So for real roots, let's recall what we showed. We showed that you have a root on the order of 1 over n away from the unit circle. And we showed that when you rescale, you don't get a Poissonian limit. So, and we are able to prove this in the case of just arbitrary mean zero variance 1 coefficients. We don't need them to be Gaussian, unlike in the complex case. So I want to just discuss quickly how you might show that you have a root near 1, and also why you shouldn't expect to have a Poissonian limit. So let's remember that we have repulsion of roots. So more specifically, if I have roots within 1 over n of each other, my value of my function here is going to be correlated. So it does not look independent on the order of 1 away. So repulsion is on the order of points 1 over n apart. So if I condition on there being a root within 1 over n of 1, it should bump down the probability that there's another one nearby. And now the only way to have real roots near the unit circle is to have a real root near 1 or a real root near -1. There isn't other room to sort of play with here. So that means that once I know I have a root near 1 and a root near -1, we should not expect Poisson-like behavior, where having another one is sort of independent of this behavior. So a quick overview of how this goes down, we just rescale our polynomial correctly. So I look on the order of 1 over n away from 1. I rescale by 1 over root n. And you get convergence to a Gaussian process. And further, it's not so bad to show that the zeros of my polynomial are going to converge to the zeros of this Gaussian process. So this handles roots near 1. And doing the same for roots near -1 is going to give us what happens for negative roots. They'll end up being asymptotically independent, so that'll give us both halves of the picture of real roots. So in order to show the existence of a real root, all we do is look at sign changes. So if I look at points very far apart, this limiting Gaussian process is going to be basically uncorrelated. And it's mean 0, so that means that the signs are going to be roughly independent. So now, if I look at a whole bunch of points that are far enough apart, that'll end up meaning they'll look roughly like fair coin flips, times some Gaussian or whatever. So now the probability to have a sign change is going to be pretty high, right? It'll look like what you should end up with if the signs were fair coin flips, which turns out to be just this expression here. And now using convergence to this limiting process shows that we have a sign change with high probability, and that shows that we do have a 0 with high probability. So now, all that's remaining is understanding the non-Poissonian behavior of these real roots once I rescale. So let's recall what Kac Rice says. It says if I look at two small intervals, and I look at the probability I have a 0 in each of these two intervals, it's some function p2xy times roughly the widths of these intervals. And a Poisson process, even just an inhomogeneous one, is going to have that these should be independent. If I have Poissonian behavior, then if I look at two disjoint intervals, what happens on one and the other is fully independent of each other. So it would have to factor here. In fact, looking at all of these Kac Rice densities and having them all factor is actually a characterization of a Poisson process. All we have to show is that you don't have this factoring occur. So what we end up showing is that if I look sort of at 0, 0 more or less, then you get that the density at 0, 0 is 0. This is just saying the probability I have two roots at a given point close to each other is going to tend to 0. This is really quantifying the repulsion that happens between roots. So the reason we don't get a Poisson process is because we have this repulsion on the order of 1 over n, and there's sort of not enough space for real roots to be more than 1 over n away from each other and still 1 over n from the unit circle. So a quick summary of our story here. We rescale to look near 1 on the order of 1 over n. This converges to a Gaussian process. If we look at faraway points, this limiting process looks roughly independent on these points. So sign changes are likely. And now, with some amount of work, the zeros of my original polynomial converge to the zeros of my limit. And the zeros of g experience a repulsion, and that tells us that our limit is not Poissonian. All right, that's all I have for you today. Thank you.
So thank you very much. And could I ask everyone to unmute themselves and give Marcus a round of applause? And if you have any questions, then just please go ahead. So one question, which is sort of maybe a naive one, but would it be any meaningful to ask for the roots at a given, or well, not at a exact given specific angle, but you know, want sort of zoom in within as a certain angle. So it would be sort of something between your first and your second theorem, right? So
yeah, so that's a good question. I think these types of results sort of only make sense when you look at a width that's like macroscopic. So if you look at it at like a sector of the unit circle that like is like a fixed size, then we know what happens in that situation. I think it's not obvious what should happen on smaller windows that are tending to 0. I'd expect this to depend on the laws of the coefficients.
Okay. Oh, there is a.
Aha, yeah. Is there some work with more untypical random variables, i.e. Cauchy random variables? Yeah, okay. So Cauchy random variables do not have a mean, but they do have a logarithmic moment. So that should mean, or let me rephrase, that means that you do in fact have convergence to the unit circle. But I'm not sure of other results beyond that. So if I were to go all the way back to much earlier in the talk, we know an if and only if condition for the roots converging to the uniform distribution on the unit circle. And you only need to have a logarithmic moment, which Cauchy random variables do have.
Yeah, just a comment on that. Is it well, maybe you know, Marcus. Do you know anything about, like, it'd be interesting, like, to if the scaling window changes, or like what's the condition on the random variable where the scaling window changes?
Yeah, that's definitely
right?
true.
So probably the 1/n business is fairly universal, but if you throw something like a Cauchy random variable at it, is it 1/n or something? I don't know.
Yeah, so I guess as Julian's sort of alluding to, a lot of this story about the typical scale has been proven only explicitly in the case of Gaussian coefficients. So, I mean, there are sort of one-directional bounds as far as what this behavior looks like, but for a Cauchy random variable, it's not necessarily even clear what the scale should be for how far away most of the roots are near the unit circle.